Okay, good morning, everybody. So today we are going to deal with the part of the course that is the last part of the probabilistic part of the course that is devoted to random vectors and mainly what we call Gaussian vectors that are just multivariate generalization of the notion of Gaussian random variable we have seen together. Okay, so let's go as usual. Okay, so let's start. Okay, so we are going to speak mainly about Gaussian vectors in this part. Okay, but I want to do some little, in fact, reminder. It's something we have done, but the idea here, since we are going to work with vectors, okay, in order to write any quantity of interest in a short way, we are going to use matricial notations, okay, in this part. So I want to do some reminder concerning this, okay? So first of all, it's not the first time in this course, okay, that we have spoken about random vectors. So we have seen previously a situation that was this one, okay? So I have x1, x2, that was a pair of random variables, okay? And in fact, a pair of random variables is just a random vector, okay, of size 2 here. We are going to generalize this today. So we have seen together that if both are discrete, okay, I can characterize, for example, the distribution of the pair by, okay, so I know that the pair is discrete if the components are discrete, and I can describe the distribution of the vector x1, x2 by the probability mass function, okay? That is the probability that x1 is equal to x1 intersected by x2 equal to x2, where I have my x1 that belongs to the range of x1 and x2 that belongs to the range of x2. Okay, so in the discrete case, working with 2 is more or less the same than working with 1, okay? And I adjust to adapt a little the definition of the probability mass function. Probability mass function that, so I can compute in general different ways. If they are independent, the probability of the intersection is equal to the product of the probability. If they are not, okay, we can use the notion of conditional probability as we have seen in the previous chapter. So we have seen together a second type of situation, that is the case where they are jointly continuous, okay? And when they are jointly continuous, it means that we have a density function for the pair that allow me to describe the distribution of this random vector in the case where they are jointly continuous. So of course, if I don't work with a pair, but with a vector of size n, I can do exactly the same thing, okay? In the discrete case, I will have to compute the probability mass function of the n tuple, okay? So this one for each x1, xn belonging to the corresponding ranges, okay? And I know that I am able to recover from the probability mass function of the n tuple using, for example, the law of total probability, I am able to deduce from this probability mass function the probability mass function of each component here doing partial sums. Exactly in the same way, in the jointly continuous case, I can define the joint density function that will also depend on n variables. Okay. So here, what is a little bit more complicated is that, for example, to check that this one is a density, I have to compute, okay, a multiple integral because I have n components, okay, so I have to compute the integral with respect to all these variables here. But once again, I am able in this situation to see that if I compute partial integrals with respect to a single variable here, I recover each density function for the component, okay? So what I have done for 2 may be done for any finite number, okay? And I can define this way all the things we have defined together. Okay, so it was just to tell you at the beginning that, okay, random vector is something that we have in fact done a little together when we have spoken about pairs of random variable, okay? So what I want to do now, in fact, is to deal with this kind of object here. And instead of using notations involving sums, for example, I want to use compact notation in order to make the statement of the result and the computations easier to do. Okay, so it's what we are going to start to do with here. Okay, so just a remark. So I make this one a little bit smaller, okay. I introduced some notation to start with because we are going to do a little bit of linear algebra here, okay. So what I denote by M of P, Q of R is in fact the set of the matrix, okay, with P lines, Q columns, and with inside here, so you have points inside in this matrix, okay, points that are in fact real number, okay. So it's a classical notation in linear algebra, and in the same way, I can define by M n of R, this one, when I have the same number of line and column here, okay, it's square matrix of size small n, okay. If I have a matrix of size PQ, we can define the transpose, okay, it's the notation I will use, okay, the transpose A prime. That is just obtained from A switching the line and the column, okay. So for example, if I take a little example, if I have A equal to this one, 1, 2, 3, 4, okay. If I take A prime, okay, I will obtain what? Okay, so the transpose matrix. So the first line becomes the first column, the second line becomes the first and the second column, okay, and this is the transpose, okay. So I will see later that I will use, okay, some tricks concerning the transpose of a matrix. Typically, the fact that if I have A prime prime, of course, I recover A. Okay, it's one property among others. Okay. We are going to work with random vectors. Okay, so just let's do the following here. So we are going to work with random vectors. So if I have a vector of random variable, okay, with values in R, I have two ways to write it. I can use the line convention or the column convention. Okay. So in fact, these two objects are the same. Okay, we have random vectors. The only thing that will change is that when we are going to multiply this term, for example, by matrix, okay, by the size of the matrix I will multiply with, okay, will depend on the convention I have used, in fact. Okay, so from now on, I will denote a random vector as a column. It should be possible to use this convention. I will use this one. Why not? Okay, so it implies that with my notation, okay, I will have here a matrix belonging to M. So I have n line and one column. Okay, so I have a vector of size n1. Okay, and we are going to consider here a random vector where the xi belongs to L2. Keep in mind that it means that the variance simply exists. Okay, so typically, and I will denote this vector by capital X here, the vector that is a column, okay, made from the x1, x2, xn that are just random variable in such a way that I can define their variance, okay? If I do the product x prime, okay, then, okay, so at the beginning I will do all the details, okay, but after, okay, you have to be fluent with linear algebra, okay? You do linear algebra, for example, in optimization, okay? So I do this product. So here I have something of size n1. The transpose matrix is something of size 1n. It implies that what I will obtain here will be a matrix of size n. And what I will have inside, I see that to obtain the coefficient at the place I, j here, I have to multiply the coefficient at the i's line here by the coefficient at the j's column here. So I obtain something of this form. The general term is xi, xj for this matrix, okay? At the line I and the column j, I have exactly xi, xj, okay? So I have this one. Typically, I have a matrix here that is a matrix that is symmetric. Because if I change the line and the columns in this situation, I obtain exactly the same, okay? Because if you switch the indexes here, you obtain a matrix that is exactly the same. Okay, so when I have a random vector, I will be able to extend what we have done in the case of a single random variable in this situation here, that is to define its expectation and its variance, okay? So for its expectation, it's that natural, okay? We are going to consider as the expectation of x. It will be a column vector where you have inside the expectation of each random variable that compose the column vector in red. in green here, okay? So the expectation will be from now on, okay, a vector of size n1, n line 1 column, okay? It's the vector of expectation. And of course, okay, when n is equal to 1, I obtain a matrix of size 1, 1 that is just, in fact, a number, okay? So I have this. For the variance, I can do exactly, excuse me. For the variance, I can do exactly the same. So if I have my vector here, my vector x1, xn, okay, we are going to define the variance of capital X as, so not a vector in this case, but a matrix, a real matrix of size n, so n line, n columns, and the term inside here will be the covariance between xi and xj, the covariance between xi and xj. Okay, so typically for n equal to 2, for example, if I have only two variables in my vector, the variance covariance matrix in this situation will be what? So for the first position here in the matrix, that is for I equal to 1 and j equal to 1, I obtain the covariance of x1, x1, that is just the variance of x1. Here, I obtain the covariance between x2 and x2, so I have the variance of x2. So the diagonal is made from the variance, and here I have the covariance between what? x1 or x2 and x1, and here the covariance between x1 and x2. Okay, so this is the variance covariance matrix in the case where n equal to 2. And from the property of the covariance, I know that the covariance is something that is symmetric. Covariance of xy is equal to covariance of yx when I deal with real random variable. And from this fact, I have in this situation, but also in this one, the fact that I obtain here a matrix that is symmetric. A matrix that is a symmetric matrix, meaning that if I consider the transpose, that I invert the columns and the lines, I obtain exactly the same matrix because these coefficients are equal, in fact. So if you change the line, okay, into the column, okay, then since these two coefficients are equal, we obtain exactly the same thing. Okay, so it's what we denote by the variance of a random vector, that is the matrix made from all the covariances this way. And I obtain this way a matrix that is symmetric. Okay? So just a last remark concerning this slide here. The variance covariance matrix, so I'll just erase here. The variance covariance matrix in this situation, as defined previously, is a matrix of size nn, where I have inside, in fact, what? The covariance between xi and xj. So I have something like this. So it's the expectation of the product minus the product of the expectations. Okay, with something that has a size nn. And in fact, I can write this variance covariance matrix, okay, in fact, using a compact notation. I can write it, in fact, simply as the expectation of what? Of the vector x minus the expectation of x. And keep in mind that the expectation is this column vector here, multiplied by x minus exponential of x transpose. I have this one here. Okay, so first of all, remark that this matricial product is coherent in the sense that here I have used a column convention for the vectors. So I have here a matrix of size n line 1 column. And here I have my transpose matrix that is of size 1n. So when I do the product of two matrices of this type, I obtain, of course, a matrix of size nn. Okay, and then I just have to remark that, okay, if I do this, x minus the expectation of x multiplied by x minus the expectation of x transpose. So the matrix I obtain inside here is just a matrix with a general term that is xi, xj minus expectation of xi, expectation of x j. So it's not true what I have written here. So I think that it's not true what I have written. So let's write it correctly. Okay, so just do the job correctly here. So I am interested in this quantity in order to prove that the variance may be expressed this way. Okay, so I just erase this one. Okay, and erase this one. So just what is x minus the expectation of x? X minus the expectation of x transpose. So I have used the column convention. Okay, so you have here on line A, xi minus the expectation of xi here. Okay, and so the transpose is something that has a j's column. Okay, I have xj minus the expectation of xj. So the matrix I obtain here is a matrix of size nn, where I have inside, so I have to do the product of both of them here. Okay, and what is the matrix for the product of both of them? So the general term in this matrix is xi, xj, this product, minus xi, expectation of xj, minus xj, expectation of xi, and the last term, that is the product of these two, that is plus the expectation of xi multiplied by the expectation of xj here. Okay, so when I do this product, I obtain this matrix. Okay, and now if I take the expectation of this term, okay, because what I want to do here, I want to take the expectation of this term to prove that the expectation of this term is just this variance here, but the expectation of this term is the expectation of this one. And when you do the computation, you have here the expectation of the product that give me, if I take the expectation of this term, I obtain this term here. And if I take the expectation of this one, I have minus expectation of xi times expectation of xj, minus expectation of xj times expectation of xi, plus expectation of xi, expectation of xj. So I have here, in fact, when I take the expectation, the same term here, here, and here, I have minus, minus, plus. That's why I obtain, doing the expectation of this one, minus the product of the expectation. Okay? So it's exactly what I have written in the next slide. That is, the variance of a random vector may be expressed compactly using matricial notation. That is the expectation of the vector, the column vector x minus the expectation of x multiplied by the transpose of this vector x minus expectation of x transpose, and I obtain this way, as I have proved previously, this variance. Okay. So we have seen here in the scalar case some property related to expectation, variance, and covariance. Okay, we know that the expectation is linear. If you have a linear combination of scalar random variable, then the expectation of the linear combination is the linear combination of the expectation. We have also seen together that the covariance is something that is bilinear, implying that, it's something that I have said, that the variance is a quadratic form, okay? And I know what are the rules of computation if I want to compute the variance of a linear combination. The variance of a linear combination is not the linear combination of the variances, okay? But I have a formula involving the covariance here, okay? So it's exactly what we are going to do in this situation here when I pass from one to a vector of random variables. And you are going to see that, of course, we will have this property that are preserved, okay, but that can be written, okay, using matrix notation in order to make them compact. Okay, so what I do here, okay, so keep in mind that I have my vector. I have my vector here, x. I have my vector x, x1, xn, and we are going to do linear combination. So to do linear combination, I will take coefficients. I will denote by small x the vector x1, xn, where here, okay, I don't have random variable inside, but I just have real number here. I am in R to the power n here, okay? If I do the product between x prime and x, what is this? So it's the line vector associated to x multiplied by x1, xn. So I do this one times this one, and I obtain the sum from I equal to 1 to n of xi, capital Xi. Okay, so this is a linear combination when the coefficients in the linear combination are given by the component of the vector small x. Okay, so this is a linear combination. So if I want to write what is the expectation of x prime capital X, okay, but I can use this one, and I know by linearity of the expectation that I will obtain the sum from I equal to 1 to n of xi, that is just a number, expectation of xi. But what is nice here is that this linear combination, and what is this linear combination? This linear combination is just a linear combination with the same coefficients here and here, but you replace xi by the expectation of xi. That is, I can write this as x prime multiplied by the vector of the expectation. So this relation here in blue is just the one that in our framework, okay, underline the fact that the expectation is linear. And so I have a consequence when I do linear combinations of components of this vector in terms of expectation, okay? So nothing new, in fact, just writing the things using matrix instead of doing, okay, scalar product here or sums. For the variance, so it's the variance of the sum. And you know that the variance is just the covariance between the term and itself, okay? And using the bilinearity of the covariance, okay, I can develop, okay, so I will have to do n square operation. And if I do this, I know from the properties of the variance that is a quadratic form that here I obtain a double sum for I and j from 1 to n of what? Of x I x j, the covariance between xi and xj. Okay, so I obtain this sum with n square terms because I have n possibility for I, n possibility for j, that give me the variance of linear combination. Okay, and for n equal to 2, you recover the formula we have seen together. And what is nice in this expression is that once again, we can express it compactly using the same kind of ID here. And I can express it compactly, remarking that these double sums is what you obtain when you do x prime, the variance of x, x. Okay, so it's a classical trick concerning linear algebra that when you multiply a matrix by here, I have a column and here the line, that is exactly the line related to this column. Okay, I obtain this double sum here as the matrix product. So keep in mind that here I have something that has one line and column, here n line and column, here n line one column. That's why when I do the product of these three, I obtain what? I obtain simply a number that is a matrix of size 1, 1. Okay, that is simply a number. Okay, so the fact that the covariance is bilinear here allow me to obtain, okay, this relation, okay, for the computation of the variance of a linear combination. So just a remark on this point. Once again. If it's not that clear for you, this, okay, you can also think about what I have proved previously. That is, previously we have seen that the variance can be expressed this way. Okay, so if I compute the variance of x prime x, I can use this one. That is what the expectation of x prime x minus the expectation of x prime x multiplied by the same transpose. So what can I do here? But first I know that this one is equal to this one. So I can factorize here by x prime. And the same, excuse me, transpose. Okay. So here we are going to use a little trick concerning transpose. Okay. When you have two matrices and when this matrix shall produce as a sense, okay, you have A, B prime that is equal to B prime, A prime, in fact. Okay. So when you compute the transpose of a product, it's the product of the transpose, but when the order is reversed between A and B here. So this one may be written as x minus the expectation of x transpose, it's my B prime here, multiplied by x prime prime, x prime prime, and x prime prime is simply x, because when you do the transpose 2 times, you come back to the initial vector. And finally, what you have in this expression, you have here expectation of x prime, x minus the expectation of x, x minus the expectation of x prime, x, and using now the linearity of the expectation. So this is a number, okay, that you can remove by linearity from the expectation. It's exactly what I have written here. And I can do the same for this one. I can remove this one from the expectation using, once again, the linearity. And you have here, you recognize the variance of x. And so it's another way to prove this one. So you have 2 ways to prove, okay? If you know a little bit of linear algebra, you know, excuse me, if you know a little bit of linear algebra, you know that here, this term is just equal to this double sum, okay? If you don't remind this, okay, you are able to use this one in order to obtain the same thing. So I just have a look on my slide because I don't know why they, okay, so I don't know, well, I will see this after, okay? So you are able to see for the moment when I will print the board, okay, to give you the PDF, okay, I will check that everything is okay. Okay, so I have this, okay, so we have proved this through relation. And in fact, I want to do the proof. So it's an exercise to do at home for you if you are not fluent with matrix, in fact. So do it here at home. So is that here, okay? I have seen how to compute the expectation and the variance of a linear combination, but it means that I have here multiply x and here multiply x by a line of size n, and I have analogous result, okay, if I multiply x, not by a line, but by a matrix of size n. So if you multiply by a matrix of size n, here you have a random vector of size nn, and you are able to develop this one using linearity, just removing the a from the expectation by linearity, okay? And here, for the variance, you do exactly what I have done here, and you just plug a of x inside this formula, and you will obtain that the variance of ax here, that is also something of size nn, okay, will be given by this one. And of course, if I take for capital A x prime, I recover this formula from this one. And if I take here capital A equal to X prime, I recover from this formula exactly this one. Okay, so it's just an extension of what I have done here in the case of general matrix instead of in the case of lines. Okay, so I have this one here. Okay, so I have seen, okay, what are the rules of computation of expectation and variance, okay, of random vectors through linear combination, okay, through linear combination. So I have this. So this one was so this slide, so okay. So it's something that we have, in fact, almost already seen together here. So keep in mind that if I have a single random variable, okay, I have defined the moment generating function of x1 at the point, let's say x1, to cope with my notation here, as the expectation of exponential of x1, okay? And we have seen together that when it exists, okay, this moment generating function characterizes the distribution of the random variable, and we have seen that we are able to compute it explicitly in the case of Poisson, Gamma, Gaussian, and so on, okay? I have also spoken about the way to define the moment generating function in the case of a vector. And I have called it m of x1, x2 at the point x1, x2 that was defined as the expectation of exponential x1, x1 plus x2, x2. Okay? And we have seen together that we have nice properties that are, if x1 and x2 are independent, the moment generating function of the pair is equal to the product of the moment generating function of each component. And in fact, I have an equivalence, because if the moment generating function of a pair is equal to the product of the moment generating function of each component, I have independence. So it's something that we have seen in the chapter concerning moment generating function. Okay. And in fact, what I will do here, so using my notation, so I have my capital X, my random vector that don't have here 2 components, but n components. Okay. And I just define the moment generating function of X at the point small x, where X, of course, small x belongs to R to the power n. I have x1, x2, xn, in fact, as by the extension of this formula, that is the expectation of the exponential of the sum from I equal to 1 to n, xi, capital Xi. And if I want, and it's what I will do in this course, if I want to use compact notation to express this, it is just the expectation of exponential x prime capital X. So you see that in the case of 1, I have this expression. In the case of n, I have in fact the same expression. The only thing I have to be careful with is that since I use a column convention for the random vectors, here instead of having x, I need to have the transpose of x. Okay? So it's the moment generating function in the case of a random vector of size n, okay, in this situation. And we have the same properties that the moment generating function characterize the distribution of the random variable, and I have the same kind of properties related to independence. Okay. So I have this one. we have seen in this case here that if I want to compute, it's a property we have seen together of the moment generating function of a of x1 plus b at the point, let's say x1 here, I can express it basically, okay, as as the following. Okay, so let's do the computation. It's the expectation of exponential of x1 times a x1 plus b that I can write as, okay, so I can remove exponential of x1a from the expectation because I don't have a random variable. And here, okay, I have just exponential of x1 times a times x1, that is the moment generating function of x1 at the point x1a. Okay. And in fact, I can prove that in this situation, I have exactly the same thing. In this situation, I have exactly the same thing, but of course, I have to adapt my notation. So consider that you have b, that is a vector of size n1, that is a column vector with n lines, okay, and a, that is a square matrix of size n. And let's see, so I am in this situation here, this one and this one here, okay, and that I want to compute the moment generating function of ax plus b at the point x. So keep in mind that here, okay, I have something that is of size n1. So I have a random vector as in this situation here. Okay, so it's just an affine transform of this vector, okay, that's transform this vector into a new one in an affine way. So if I use my definition here, it's the expectation of exponential x prime a x plus b. Okay. Once again, here I can remove this part because b is not a random vector, it's just a vector. So I have exponential x prime b. Okay, multiply by what? But multiply by something that I can write as the expectation of exponential x prime a capital X, that I will denote as expectation of exponential of a prime x prime multiplied by capital X. Okay, because I use what I know about the transpose, a prime x transpose is just x prime times a transpose transpose, that is equal to a. And why I do this? Because this way I cope with my definition here to see that here I have exponential of x prime b multiplied by the moment generating function of x at the point a prime x. So I have the generalization of this formula here, but in the case of a random vector. So if I know the moment generating function of a random vector, then I am able to compute this way, when it exists, the moment generating function of an affine transform. Just be careful in my slide here. Not a misprint, but something that can be a little bit more precise, because here, this term here is just equal to exponential x prime b, because exponential x prime b is a constant, so I don't have expectation inside. Okay, it's just exponential of x prime b. Okay, so I have these rules of computation for the moment generating function of a random vector and the way to compute it if I do affine transform. Okay. So it closes what I want to remind for random vectors, okay? And we are going to use this, okay, to start with what I want to do more deeply in this course, that is to extend in a multivariate way what we have defined as a Gaussian random variable, okay? So I continue. So this one is the same slide as previously, so I can erase it. Okay, and I keep this one. Okay, that will be my definition of a Gaussian vector. Okay. How is defined a Gaussian vector? So a priori, okay, if I ask you to propose what may be a natural definition of what is a Gaussian random variable in dimension 2 or in dimension 3 or in dimension 4, a natural answer should be, okay, why not a Gaussian vector being a vector for which the components are just Gaussian random variable? Why not? It's a possible definition. But unfortunately, okay, if you use this definition, you will be able to do nothing. No general things, okay, and you won't be able to extend, okay, what we have for a single Gaussian random variable and what we have for a single Gaussian random variable. We have several things. We have first the fact that we know explicitly its density function, okay, 1 over the square root of 2 pi sigma square and so on, okay. We have also the moment generating function that is perfectly known, okay, that is exponential Tm plus sigma squared T square over 2, okay? So I have a nice expression for the moment generating function in the case of a single Gaussian random variable. And if I want to have these properties for my multivariate extension, if I take as a definition of a Gaussian vector, a vector for which the components are Gaussian, I won't be able to obtain this. I won't be able to obtain this. Okay, so that's why, in fact, as you are going to see now in the definition 27, what we define as a Gaussian vector is something that is a little bit more complex than what I can naively propose, that is a vector with Gaussian component. It's not this one, it's something that is a little bit more restrictive in order to be able to obtain the properties we want to extend from n equal to 1 to general n. So the way to define a Gaussian vector is this one. A Gaussian vector that you can also find in textbooks are something called multivariate normal distribution. So that is normal distribution in a dimension strictly higher than 1. So a Gaussian vector is what? Okay, is a vector for which any linear combination of the components is a Gaussian random variable. So a Gaussian vector is a vector for which any linear combination of the component is a Gaussian random variable. So I have used words in order to describe this proposition, but here it's exactly what I have written here. Okay. If I start from my Gaussian vector, from my vector x1, xn, we have seen together that if I want to do linear combination with coefficients small x1, small xn, okay, the sum of xi, capital Xi, from I equal to 1 to n can be written as x prime capital X. So I will define a Gaussian vector. So I repeat the definition I have proposed is a random vector for which any linear combination of the component are Gaussian, and any linear combination is something of this form. In fact, so a Gaussian vector will be a random vector for which for all x of this form, x prime x is a Gaussian random variable, and you have here this definition. Okay. Okay, okay. Just a remark before to see some examples. I say that if X is a Gaussian vector, then for all I belonging to one n, xi is Gaussian. So I said that if I impose for capital X to be a Gaussian vector, that is any linear combination of the component is a Gaussian random variable, I said that necessarily the component of my vector are Gaussian. The component of my vector are Gaussian. So why I have this? But typically, if you take for X the following vector, so you have 0 everywhere, except a 1 here at the ice line. And if you do x prime x here, you obtain simply xi, implying that if I am a Gaussian vector, any linear combination of my component are Gaussian. And so if I take this particular linear combination, I obtain that each component of the vector is Gaussian. But be careful, okay? I have this implication. If I am a Gaussian vector, then my components are Gaussian, okay? But I don't have the converse. It's not sufficient to have this to obtain the Gaussian vector. So this one is false. Be careful. It's not sufficient to have components that are Gaussian to be a Gaussian vector. The definition of a Gaussian vector is more restrictive, okay, in the sense that, okay, any linear combination of the component have to be Gaussian, not special linear combination that are the one that will give the components. But of course, I have the converse. If I am a Gaussian vector, my component are Gaussian, okay? So we are going to see a counterexample of this implication, okay, later on. But don't think that a Gaussian vector is a vector with Gaussian component. It's a vector for which any linear combination of the component is a Gaussian vector, okay? So let's continue doing the two little exercise or example, in fact. Here. So I have my definition of a Gaussian vector here. So I said that there is a situation, okay, where it is very easy to obtain Gaussian vector. So it's the example 1 here. So suppose that you have x1, xn that are independent Gaussian. Okay, so they are more than Gaussian, they are Gaussian and independent. I said that in this situation, x1 xn is a Gaussian vector. So you can build a Gaussian vector if you start from Gaussian random variable, but it's not enough, Gaussian random variable that are independent, okay? So why I have this, but if I take x prime x here, it's linear combination of the xi. And we have seen together that when I have independent Gaussian random variable, if I do linear combination by independence, I know that x prime x is Gaussian. if I have independence. If I don't have independence, I can't conclude, okay? But here in my statement, I have independence. So if you build a vector made of independent Gaussian random variable, you will obtain a Gaussian vector. But be careful, it's not the only situation. You will have situations where, and as we are going to see in the next example, you will have situations where you will have Gaussian vectors, but for which the component won't be independent. So if you start from independent Gaussian, you build easily a Gaussian vector. The converse is false in general. That is, if you have a Gaussian vector, in general, the components are not independent. It's possible to have components that are not independent. So it's exactly what we are going to see in the second example. So let's do this way. I have this one, I erase. So I suppose that y1 and y2 are two independent and 0, 1. So y1 is independent of y2, and y1 and y2 are and 0, 1. Why not? I define x1 this way, and I defined x2 this way. I want to prove two things. First, I want to prove that, so I know that here, from this one and from the example one, I know that the vector y1, y2 is a Gaussian vector because it is made of independent Gaussian random variable. Okay? So what I have here, I define, in fact, a linear transform of this vector this way, y1 minus y2. I want to prove that first, that x1, x2 is a Gaussian vector. Okay, so to prove that I am a Gaussian vector, I have to prove that any linear combination of my components are Gaussian. So I have to consider for any x1 and x2, I have to consider x1, capital X1, plus x2, capital X2, and I want to prove that I have something that is Gaussian. And of course, we are going to use the definition of x1 and x2 in order to compute this. So it's x1, y1, plus x2, y1 minus y2. So something that I can write this way, it's x1 plus x2, y1 plus, okay, minus x2, y2. And in order to prove that x1, x2 is a Gaussian vector, I have to prove that this linear combination is a Gaussian random variable. And of course, I have this because, okay, y1 and y2 being Gaussian and independent, of course, okay, this one follows the Gaussian because of star, where star is my set of hypotheses here. Okay. So this linear transform of a Gaussian vector is a Gaussian vector. And of course, it's something that is in fact more general than what I have proved. If you start from a Gaussian vector, if you take a linear transform of this vector, of course, the new vector you will obtain will be a Gaussian vector. Okay, it's something that we are going to prove just after. Of course, we have this because, okay, linear combination of linear combinations are in fact just linear combination. It's the argument. But here I have proved, okay, directly this fact in my special case. So I have a Gaussian vector. x1 and x2 is a Gaussian vector. And I have to prove that they are not independent in order to show you an example of a Gaussian vector where I don't have the independence between the random variables. So I have to prove that x1 and x2 are not independent. So I can try to compute, for example, the covariance between x1 and x2. And what is the covariance between x1 and x2? It's just the covariance between y1 and y1 minus y2. And using the fact that by covariance is bilinear and y1 and y2 are independent, this one is just the variance of y1 that is equal to 1. So I have something that is different from 0, implying that x1 and x2 are not independent. They are not independent. Okay, they are not independent because their covariance and the covariance is not equal to 0. Okay, so we have seen the definition of Gaussian vector. Any linear combination of the component is a Gaussian random variable. Then I have tell you that if I start with independent Gaussian, of course I will obtain a Gaussian vector. Okay, if I take these random variable as components, because I use the property concerning linear combination of independent Gaussian random variable. But this is not the only case. You have cases of Gaussian vectors, okay, where of course the components are Gaussian because it's mandatory, in fact, but where the random variables are not independent. And it's typically the example we have seen together here. Okay, so we have this definition, and now we are going to work a little. That is, what is to work a little? In the case of a Gaussian random variable, okay, so maybe I can add this here. If you have x1 that follows the n sigma square, okay, we have seen several things together. We have things that, okay, three things, let's say, together. First, that I am able to know the density function. Okay, this classical expression here. And of course, my sigma square has to be different from 0 if I want to write this. I have the moment generating function of x1 that we have computed together. And we have also see together the stability by a fine transform. That is, if I take a x1 plus b, it follows, okay, n a m plus b a square sigma square. Okay, so we have proved these three things in the case of a single Gaussian random variable. And what we are going to try to do now is to extend these three properties in the case of Gaussian vectors. We are going first to prove that I am able to find the moment generating function of a Gaussian vector. And you are going to see that the result we are going to use is this one in order to prove this result. Then we are going to be able to prove that we have the stability of Gaussian vector by a phi transform and find explicitly what are, okay, the analogous of these two quantities here. And finally, that in some situation, that is the analogous of the situation where sigma square is different from 0, we will be able to compute the density function of a Gaussian vector. Okay, so it will be what we are going to do now. So first, interested in the moment generating function of a Gaussian vector. Okay, so it is this proposition here. that tell me, so I will do two things at the same time in this proposition. First, that I have the moment generating function of a Gaussian vector given by this expression here, and I will comment just after. I will introduce a notation because in fact, I will see that the moment generating function of a Gaussian vector only depend on the vector of the expectation and only depend on the variance covariance matrix of this vector. And so I will introduce this notation. A Gaussian vector has a distribution perfectly characterized by its expectation and its variance covariance matrix. Okay, so exactly what we have done in the case of a single that we will be able to extend in the case of a Gaussian vector. And in the second step, okay, I will prove that. So I have done a little misprint in this slide, so I will just correct here. I will just correct it. So I just excuse me, small. I have done a little misprint in the slide here. It's not X that you have here. It's a X plus B that follows this one. Okay, and we have in this proposition exactly the analogous of this one in the case of a single, but adapted to my situation and with my matrixial notation. And that's why I have spent time at the beginning of the session, okay, in order to do some reminder on the way to write compactly using matricial notations, okay, the rules of computation in the case of the expectation and in the case of the variance for Gaussian vectors, okay? Okay, so let's do the job. So I will do the job. That is first to compute the moment generating function. Okay, so first keep in mind that what I have defined as the moment generating function of x in the vectorial case is just the expectation of exponential of x prime x. Okay, when okay, x is a vector of r to the power n. Okay, what can I say about x prime x? Capital X is a Gaussian vector. Okay, capital X is a Gaussian vector. If I come back to the definition of a Gaussian vector is a vector for which any linear combination of the component is a Gaussian random variable, and any linear combination of the component may be written as x prime times x, where x is this column vector made of constant. So in our situation here, that is not this one, that is this one here, I know because x is a Gaussian vector, so x is a Gaussian vector. So x prime x follows a Gaussian random variable, for sure. Okay, so I have a Gaussian random variable, and if I want to fill the gap here, I just have to compute the expectation of x prime x. But we have seen together that the expectation of x prime x by linearity is just x prime, the expectation of x. And I have also to compute the variance of x prime x. And we have also seen together that this variance may be expressed as x prime variance of x, x. So it means that I know perfectly the distribution of this term, that is a Gaussian, with an expectation equal to x prime exponential expectation of x, x prime variance of x, x. Okay, so I have this. Okay, and I want to compute this term. But what is this term? Here I have a random variable that is Gaussian. I can write this expression as the moment generating function of this Gaussian random variable x prime capital X at the point 1. Because, okay, if I define x prime X as the random variable, I have here just 1 time this quantity. And it's exactly the definition of the moment generating function of the random variable x prime X at the point 1 here. But I will continue my computation here. But I know what is the moment generating function of a Gaussian. Okay, it's something that I have reminded to you here. The moment generating function is given by this expression. So for t equal to 1, it's just the exponential of the mean plus sigma square over 2, where sigma square is the variance. If I use this result here, I have exponential of the mean plus sigma square that is given by this expression here, x prime variance of x over 2. And you see that the relation I have obtained here is exactly the relation I want to prove here. So you see that the computation is very basic in this situation. And it's very basic because we have the good definition for being a multivariate extension of the Gaussian. Because this linear combination here is Gaussian, okay? I am able to characterize exactly what is its mean and its variance using my rules of computation, using matricial notations. And then from what I know in the case of a single random variable, I am able to deduce what happened in the case of a Gaussian vector. So the moment generating function is given by this expression this way. And that's why we are going to use this notation for a Gaussian vector, because as in the univariate case, a Gaussian distribution in the univariate case may be characterized by two numbers, the mean and the variance. In the case of a Gaussian vector, okay, I see that the moment generating function is perfectly known if I know the vector of the expectations and the variance covariance matrix. That's why I use this notation, because if you know that you are a Gaussian vector, if I give you the vector of the expectation and the variance covariance matrix from the form of the moment generating function, you know that these two matricial quantities will uniquely define your Gaussian vector. And so we will say that X follows a Gaussian with a random vector expectation of X and a variance, that is the variance of X. Okay? So in fact, basic extension of what we do in dimension 1. But it's possible because we have the good definition. If I had defined a Gaussian vector as a vector for which components are Gaussian, I won't be able to do this kind of computation. Okay, it's not possible. It's because I have defined a Gaussian vector as a vector for which any linear combination of the components are Gaussian. So it remains to do the second things here. Okay, that is to prove that a Gaussian vector, or to be a Gaussian vector, is something that is stable by affine transform. So here I reduce, and don't forget that there is a little misprint in this slide here. That is here, it's not X that I have, but AX plus B. Okay. Okay, so let's do the job. So in order to prove that, so I start from X, that is a Gaussian vector with a mean vector denoted by expectation of X and a variance covariance matrix that is denoted by variance of X. And I am interested in AX plus B, where here I have something that is a vector, not a random vector, but a vector, n line, 1 column. Here I have a matrix of size nn, but inside I have numbers. I don't have random variables. And here I have my random vector of size n1. Okay, so it means that here I have a random vector of size n1 using, okay, the product rule computation of matrix. Okay, so if I want to find its distribution, okay, but we are going to define what is the moment generating function of this one, okay, at x, for x belonging to r to the power n. But if you come back to what we have done earlier, so it was maybe, I don't remind, it was here maybe, yes, I have proved this one, that is, okay, if I start from a random vector, how to express the moment generating function of an affine transform from the moment generating function of my vector, and it's exactly this quantity that I have to use, okay, and it's the one we are going to use here, so that is this one here. This is what, okay, so this is exponential of x prime b, okay, plus, time, the moment generating function of x at the point a prime small x, okay? Something that has nothing to do with the fact that I am Gaussian or not, okay? This equality is always true once the moment generating function exists. So I have this. What can I do now? But I can use what I have proved before, that is to use this one. I know what is the moment generating function of capital X. So I continue my computation here. I have exponential of x prime b. So this moment generating function that can be computed this way. So I will do the computation. So I have a prime x prime, okay, expectation of x, okay, plus a prime x prime variance of x a prime of x over 2. And now we are going just to use the properties of the transpose. So a prime x prime is equal to x prime a prime prime, that is just x prime a multiplied by the expectation of x, plus, and the same for this one, it's x prime a prime prime, that is just x prime a variance of x a prime x over 2. And what I can remark that my moment generating function can be written this way: exponential of x prime of b plus a expectation of x plus x prime a variance of x a prime x over 2. And what I can deduce that in fact my moment generating function has exactly the same form of the one I have previously computed here. And I can deduce that a x plus b is a Gaussian vector. So what is the mean? But the mean is the term in front of x prime here in this expression, that is exactly this one. So b plus a expectation of x. And I have here the variance covariance matrix. That is what I have in fact between x prime and x, and what I have between x prime and x here is this one. That is a variance of x a prime, and I have proved exactly this result. So when you linearly transform a Gaussian or affinely transform a Gaussian vector, okay, you obtain a new Gaussian vector and you know exactly what are its characteristics. Okay, so it's exactly the analogous of this property here. Excuse me, what I have done here. No. This one. It's the analogous of this property, but when x1 is no more a single Gaussian random variable, but a Gaussian vector. Okay. So I have this. So before to continue, okay, with the properties of the Gaussian vector, let's see what happened from a geometrical point of view. Here, what I have done, I start, okay, with capital X. This one, okay, and I suppose x1 and x2 to be independent, and x1, x2 that are n01, okay? And what I have plot here, I have plot, okay, realization of this random vector. So I have plot pair of Gaussian random variable, okay? And I have done the plot of 5,000 pairs of n01, okay? And the way I have generated, okay, pair of independent n01, it's what we call the Box-Muller method. That is, if I remind, a little exercise in the list 5 of exercises, okay? So just maybe have a look on this. So I just want to show you the thing, okay? So if I come back to the list 5 of exercise, my website, no, it's not this one. I want to go to my website, this one, QM part. I have the list 5 of exercise here. So it's not this one, it should be the list number 6, maybe. It's this one here. The exercise 4 of the list 5 or the list 6, okay, so I don't have corrected this one, okay, because the computation of the Jacobian matrix, okay, it's not tricky, but okay, I don't want to spend time on this one, but the result is important, in fact, more than the proof. And what is this result of exercise 4? It tells you how to generate a pair of independent n01 from two independent uniform on the interval 0,1. And why this result is interesting in practice? Because, okay, to generate uniform on the interval 0,1, in general, okay, in any computer, you have a way to do this. That is the random function of your computer. That is, okay, a command that allows you to choose randomly a number between 0 and 1. If you do this twice, you obtain in general two independent realization of a uniform on the interval 0, 1. And this little exercise 4 here just tell you that if you start from the two uniform, if you transform them this way, it's very simple transformation involving logarithm, cosinus, and sinus here. Okay, so you have a closed form expression. Okay, then the pair G1, G2 that you obtain is a pair of independent Gaussian random variable. So if I want to generate G1 and G2, my two independent n01, I just have to use 2 times the random command of my computer in order to have U1 and U2. And applying this formula, I can do I can do the job. Okay. So it's exactly what I have done in order to plot this thing here. I have generated, in fact, okay, 5,000 pairs of uniform on the interval 0, 1 using random functions, okay? Then I have used the transform of the exercise 4 of the list 6 in order to generate, okay, 5,000 pairs of independent and 0, 1, okay? Then I obtain this plot here, and you have here what a random Gaussian vector looks like, okay, if it is made of two independent n01. So just a remark concerning the geometrical aspect of this one. So as you see, okay, it's like if I see a circle, let's say, okay, kind of circle. If I have a look on my variance covariance matrix here, okay, what is the variance covariance matrix in this situation? So I have independent, so the covariance is 0, okay, but the variance of each of them is equal to 1, okay? And in fact, if you have a look on this matrix, okay, so it is a matrix that is diagonal, okay, there is one n-gain value that is 1, okay? And I can see that I have two n-gain vectors, okay, that are 1, 0, 0, 1. I have n-gain vectors for, excuse me, for lambda equal to 1. That is the n-gain value 1 here. And I see that what are these vectors? Okay, so if I want to, I see, in fact, it's just to tell you that I see that I have two interesting direction here. If I denote this vector by u1 and this vector by u2, okay, you have u1 that is here, and you have u2 that is here, and I see that, in fact, I have these two natural direction here, and I have a kind of circle here, and I can see that the distance here and the distance here is related, in fact, to the eigenvalue of, okay, my variance covariance matrix here, okay, in the case of independence. And since I have a single n-gain value here, but the distance here are equal, so that's why I have something that looks like, in fact, a circle here, okay? Let's see another example. Here, okay, it's once again a Gaussian vector, but it is not made of independent Gaussian random variable, okay? My covariance matrix in this situation is given by this one. Okay, why not? And here it's a Gaussian vector that is also centered, mean equal to 0. So when I see this, okay, so it looks like different. It's more an ellipse than a circle here. Okay, but I see that I have two, okay, typical direction here that are, okay, so excuse me for this, okay, the picture, that are the axis of the ellipse, in fact, something like this. Okay, and once again, I can see that I can find the n-gain value of this matrix, find the related n-gain vector, and then the n-gain vector will give me these two directions that are, in fact, the two direction of the two axes of my ellipse in this situation. And the distance here will be related to the n-gain value related to this n-gain vector, and the same for this one. And in this situation here, okay, the n-gain value are not the same, contrary to what happened in the previous case. So that's why I don't have a circle in this situation, but I have an ellipse. Okay, so when you don't have a circle anymore, it means that the involving Gaussian random variable don't have the same variance, or more precisely that the variance covariance matrix has two eigenvalue that are different, okay? And secondly, these two axes, okay, that are the natural basis, okay, when the random variable are independent, as in this case, okay, are transformed, okay, in the sense that they are the in-gate vectors of the variance covariance matrix. Okay, so it was just to show you how you can plot Gaussian vectors and what they look like, okay, in a very basic situation. Okay, it was just to show you this. Okay, so let's continue, okay, with what I have done and what I can obtain from the definition. So first, 2 remarks. If I start from independent and 0, 1, of course, as I have previously said, in the case of independence, I am sure that this vector is Gaussian. If I want to characterize it, I have to characterize the vector of the expectations. In this case, I have a vector that is just the null vector of r to the power n, because each of them has an expectation equal to 0. And I have also to give explicitly what is the variance of x. Since they are independent, if I take the covariance between two difference, I obtain 0. And if I take the covariance of x1 and x1, I obtain 1. That is the variance. Covariance of x2 and x2, I obtain 1, and so on. So here I have the identity matrix of size n, 0 outside the diagonal and 1 inside, and I denote just this matrix as the identity, so I for identity, and in size n. So that's why I have here I of n. Okay, so if you have n independent n 0, 1, the vector you obtain from my previous proposition is just a Gaussian vector for sure, with an expectation that is 0 and a variance that is identity. Okay, so now what happens if I transform linearly this vector? If I transform this vector linearly, what I obtain? I can use the previous proposition that tell me if I transform linearly a vector, okay, I obtain this one. In my particular situation, the expectation is equal to 0, so I don't have such a term here. And my variance covariance matrix is equal to identity. So finally, okay, if I apply the proposition 25 statement B, I obtain for this one, the proposition 25 small b, I obtain a Gaussian vector with a mean that is simply equal to b, because the expectation of x is 0, and a variance covariance matrix that is A times A prime. Okay? So just a remark concerning this one, because more than the result that is very basic to prove, that is a consequence of this proposition here, we have a consequence to this one, a consequence that will explain to you how I have plotted this one. I have explained to you how I have plotted this one using the result of the exercise 4 of the list 6 of exercise, okay? Using the Box-Muller methodology in order to obtain from 2 uniform, 2 independent and 0, 1. Here, I don't have explained how I can find, okay, a Gaussian vector with that is centered and with this particular variance covariance matrix. Okay, so let me just tell you a few words about this topic here. So maybe I can do this. So suppose that you want to generate, so I want to generate X that follows the N, okay, expectation of X, variance of X. Using a computer, you want to generate independent realization of this one, exactly what I have done this, in this case, okay, for an expectation that was 0 and a variance covariance matrix that is given by this, okay? So what is the methodology to do this? But in fact, the methodology is, in fact, to start from Y, that is the Gaussian vector y1, yn, where they are all the yn, y1, yn are independent and are also independent and n01. Okay? So what I know from my previous result, if I transform linearly my y, I obtain this vector here. Okay, so for A belonging to Mn of R, and for B belonging to Mn1 of R, we have proved that A y plus B follows the N B and a vector that is a variance covariance matrix here that is A times A prime. Okay, so it's exactly what I have done here. Okay, that is the result of this remark here. Okay, if I do this, what happened? But if I want to generate, so I am able to generate this one. So this one, I can do this one with a computer because I have independent and 0, 1 to generate. I am able to do this from the exercise 4 of the list 6. I am able to do this starting from uniform, that is from the uniform command of my computer. So I am able to generate this one, able to generate. So if I am able to generate, I am able to generate this one because I just have to apply the transform that is an affine transform. If I know A and B, I will be able to generate explicitly this one, okay? But if I want to generate this one, I need that my B is equal to the expectation of X. So no problem for this one because I have to take for this one simply the expectation of X. And I need to solve this one, A prime equal to the variance of X. A prime that is equal to the variance of X. So it means that if I solve these two equations, so the first one is immediate, but if I solve the second one, that is to find A such that A transpose is equal to the variance of X, okay? If I apply this formula here, what will be the distribution of this one? It will be just the distribution of expectation of X, A times A prime, that is just the variance. So it's the way to generate a general Gaussian vector from this particular one, that is the Gaussian vector with mean 0 and variance covariance function that is equal to identity. And in fact, so it won't be the purpose of my course today, but it is possible to find such an A. Okay, so possible to solve it explicitly. Possible to solve it explicitly. Okay, in an efficient way. And it's exactly what I have done here. To generate this one, what I have done, I start from 2 independent and 0, 1, and I have found a matrix A such that A times A transpose is equal to this matrix here, and I use the linear here transform in order to generate from 2 independent and 0, 1 some realization of this Gaussian vector and to obtain this plot here. Okay. So there is a last thing to see in this slide here. That is probably, okay, the most famous and interesting property concerning Gaussian vectors, okay? So keep in mind that when I have defined the covariance, I have said to you that be careful because I have the following. Independence implies covariance equal to 0, but in general, I don't have the contrary or the converse. That is, if the covariance is equal to 0, I can't deduce a priori that x1 and x2 are independent. So if I remind, I have given to you a counter example concerning this point, but if I don't, okay, you will see that in the list 8 of exercises, okay, you will have a little exercise where I will show you how to build a random variable with a covariance, or a pair of random variables with a covariance equal to 0, and where these random variables are not independent. Okay, so I don't remind which exercise, so I can recover. Okay, this, I have the list somewhere here. You will see that, okay, it's in the list of exercise that I will give to you. Then you have the exercise 4 of the list 8, where you will have, okay, so keep in mind that this one is not true in general, okay, so this one is always true. Always true. And for this implication that we are going to prove, it is related to the fact that I have Gaussian vector. If I don't have, if I am not, okay, so this one is not true in general. And you can see for this, the exercise 4 of the TD8. Okay. So I have this. So we are going to do this proposition here, and to prove this proposition that tell me that in the case of Gaussian vectors, okay, if I have x1, x2, that is a Gaussian vector, if the covariance is 0, then I have independence. So Gaussian vectors are random vectors that have nice property, okay, in terms of independence with respect to covariance equal to 0. Okay, so, and a priori, it's easier and easier to prove that the covariance is equal to 0 because it's just a little computation than to prove that you have independence directly. Okay, so let's do the proof. You will see that the proof won't be complicated here. So make it small. So as I have said here, as I have said, this implication is always true. So I am interested in this one. Okay. If the covariance is 0, then I am independent. Okay. So let's write this Gaussian vector here. And we are going to introduce some notation. So I have a Gaussian vector, so I know that it is characterized by the vector of expectation, that is mu1 here, mu2. Okay, why not? And the variance covariance matrix. And in my situation here, the variance covariance matrix is what? But I know that the term covariance of x1, x2 is equal to 0. So I have a matrix that is diagonal, in fact, here. And here I will have sigma 1 square, that is the variance of x1, and here sigma 2 square. And now let's compute the moment generating function of the pair x at the point x1, x2. Okay, so this one will be denoted by x and consider as usual, a column vector. So I have the expression for this one, the expression that was given by, that was given by the proposition 25, that is, okay, if I know the vector of the expectation, the variance covariance matrix, I have the moment generating function. So this moment generating function here is equal to what? So it's equal to the exponential of x prime, expectation of x, okay, plus the following, plus x prime, variance of x over 2. And what is nice here is that my variance covariance matrix is diagonal here. So I can do this computation very basically here. I will obtain exponential of x1 mu1 plus x2 mu2 plus this term here that is simply in the case of a diagonal matrix, okay, x1 square sigma 1 square plus x2 square sigma 2 square over 2. And in fact, what I can see here, I can see that I can separate, okay, this quantity in a product of one quantity depending only on x1 and one quantity depending only of x2. Okay, so it implies the independence, and I have something that I can write as simply the moment generating function of x1 at the point x1 multiplied by the moment generating function of x2 at the point x2, and something that implies from the part concerning moment generating function, the independence between x1 and x2. Okay? Independence between x1 and x2 that is given computing moment generating function. Okay, so it's that natural to use this point of view here to prove my result, because I have seen in proposition 25 that I have a nice expression for the moment generating function of a Gaussian vector. And I know that there is an interesting relation between independence and moment generating function, okay, of pairs. So it's what I use. Okay, so maybe now I will do a little break, okay, and I will continue in few minutes here. Okay, so see you. You will see nothing in the video, but I will do a little break to have a coffee. Okay, so let's come back to the course. Okay, so what we have finished with. So I have proved the fact that for Gaussian vectors, okay, and keep in mind that it is only in this case that if the covariance is equal to 0, then I have the independence. Okay, so a property that is really nice in the framework of Gaussian vectors, and you have the proof of this result here. I have this one here. Okay. So now we are going to finish the part concerning Gaussian vectors. Okay. So keep in mind what I have said to you previously. I have said to you that when I have, excuse me, when I have a single Gaussian random variable, okay, it may be characterized by its moment generating function, and we have extended this property in the case of Gaussian vector, okay. I have the stability by phi transform by something that I have also extended in the case of Gaussian vector, and it remains the last point, the one concerning the density of x1, okay. And now what we are going to see together is that, okay, if I have a Gaussian vector under a condition that is the analogous of this one, and because keep in mind that when you have a look on the density of the nm sigma square, since you have to divide by the absolute value of sigma, my sigma has to be different from 0 here, okay? So under the analogous of this condition here, that will be a condition on the variance covariance matrix, I will have this kind of density for a general Gaussian vector. Okay, so let's have a look on this part. That is this one. Okay. So we have two results, okay, concerning this point here. First, the fact that, so I just, let me once again, okay, I just want to be sure that, okay, it films correctly. Yes, it seems to. So if you have a general Gaussian vector, okay, here, excuse me. So if I have a general Gaussian vector, if I suppose that the determinant of sigma, so I have a matrix here, the variance covariance matrix, if the determinant of sigma is different from 0, meaning that sigma is bijective, then, okay, I have this expression for the density function of my Gaussian vector. Okay, so let's comment this. Okay, so first remark. So for the proof of this proposition, I will do it for n in the video of the tutorial number 8. You will see that it's what I have called exercise 0 in the list 8. And you will see that I will do the proof in the case n equal to 2, okay, of this result here. And that is just the consequence of the proposition 16 here. And the one with H1, H2, G1, G2, the Jacobian, and so on, okay? So have a look on this one, okay, to have the proof of this proposition for n equal to 2. And for a general n is just, okay, something that is based on an extension of the proposition 16 for n strictly greater than 2. So if I have a look on this density here, so keep in mind that when n is equal to 1, okay, so if I consider that x follows n b sigma here, I have, in the case where n is equal to 1, I have for b and sigma here, I have numbers. Okay, I have numbers. And in this case, the density I obtain, if I use this formula here, so for n equal to 1, I have 1 over 2 as a power here. So it's 1 over the square root of 2 pi, 1 over the square root of the determinant of sigma, but the determinant of sigma here is just sigma itself because I have a number. So it is 1 over the square root of the variance, in fact, sigma square, with my previous notations. And I have the exponential of what? So I have the exponential of this matricial product, but keep in mind that here, all these three terms here, are numbers, okay? So in fact, if I do the product, it's a classical product, okay? It's a classical product between numbers, and I obtain minus 1/2. So x minus b times sigma minus 1 times x minus b. Here I have three numbers here that I can write as x minus b square over sigma. 1 sigma minus 1 here is just 1 over sigma, and you obtain, okay, with my classical notation with b equal to m and sigma equal to sigma square, but the density of n b sigma or n m sigma square. So what I have here is just a generalization of what you obtain for n equal to 1, okay? It's just this one. Second remark concerning the statement A of the proposition 27. suppose that if you suppose that my variance covariance matrix here is a matrix that is diagonal. So suppose that you have 0 outside the diagonal, okay, and that you have sigma 1 square, sigma n square here. And if I denote by B, the vector of the expectation, that I will call it mu1, mu n here. Okay, so in this particular situation, okay, what is the determinant of sigma? The determinant of sigma is just sigma 1 square, sigma n square, sigma minus 1, I have a diagonal matrix here. So it is just 1 over sigma 1 square, 1 over sigma n square. And so, okay, if I do the computation and do it at home, okay, it's just a little computation concerning matrix. My density function, I will be able to write it this way. So I will have 1 over the square root of 2 pi to the power n. That is the term here. Okay. I will have 1 over the square root of the determinant, that is just the product of the sigma square. And then I have a term here that is what? That is just exponential of minus 1/2. And here, okay, sigma minus 1 is equal to this diagonal matrix here. I have 0 and 0 here, okay? And I have just term on the diagonal here. So I have, for this term, I have simply the sum from I equal to 1 to n of something of the form that is xi minus mu I square over 2 sigma I square. And what I will find in this situation, that the density of my Gaussian vector is simply the product of the x1 here, the density function of each component. Because if I have a variance covariance matrix that is diagonal according to the previous proposition, it means that my x1, xn are independent, and so the density of n of the n tuple here is just the product of the density of each component. So you have inside this formula, okay, this formula contain also information for sure when x is made of independent x1, x2, xn, okay, and in this situation I recover from this formula the fact that the density function of my n tuple is equal to the product of the density function of each component, okay? So I repeat that for the proof of this result, have a look on the end of the tutorial number 8, okay? And you can see this proof for n equal to 2 as a consequence of the proposition 16 in the course. Just a remark also before to pass to the statement B, concerning this quantity here, the square root of the determinant of sigma. A priori, okay, if I want to consider this quantity, I need that the determinant of sigma is a positive number, okay? Or it's meaningless to consider the square root. And in fact, so I won't spend too much time, okay, on this because I will do it at the end of this session. So here I said that the square root of delta is well defined because the determinant of sigma is positive. And I will explain to you why the determinant of sigma is positive at the end of the class when I will do, okay, some complementary material. See, end of the class, okay? So for the moment, I admit this. And I will do some remark, because in fact this remark will be interesting, okay, in several points, okay. So I will do a particular big remark at the end of this session. So in order to conclude, okay, what I have written in my slides, okay, I just have to focus on the statement B of proposition 17. So what is this? So here the idea is to have a look on the relation between Gaussian vectors and conditional expectation. Okay, so suppose that x1, x2 is a Gaussian vector with this characteristic here. Okay, I said that we know what is the conditional density of x1 given x2 is equal to 2. So given x2 is equal to x2, then x1 follows a Gaussian random variable, okay, given by this expression here, okay? So I will do the proof of this result, okay? But at this stage, I just want to show you that this conditional distribution is a Gaussian one. So typically, if I want to compute the conditional expectation of x1 given x2, I know that it is a function of x2, where this function is given simply by the expectation of this conditional distribution here. Okay, so if I admit this result here, my star is equal to what? But the expectation of my Gaussian is given by this expression here, so I will have mu1 plus ρ1 2 sigma 1 over sigma 2 capital X2, because I plug inside this expression capital X2, minus mu2 here, mu2, not mu3. Okay, and what I can see from the fact that my Gaussian density is given by this expression here is the fact that this conditional expectation is, of course, a function of x2 as defined in the course concerning conditional expectation here, but this function has a very particular form to be affine in capital X2. And I see in this very particular situation, that is the situation of Gaussian vectors, that when I want to compute the conditional expectation of one component with respect to the other, this conditional expectation is linear in X2. And in fact, I obtain, in this case, what I have called at the end of the course concerning conditional expectation, the optimal linear predictor. So what you need to keep in mind for Gaussian vectors is that when you are going to compute the conditional expectation of one component with respect to another one, you will obtain something that will be linear, okay? And conditional expectations in this case will just be optimal linear predictor, okay, as defined at the end of the course concerning conditional expectation, okay? So we are going to do the proof of this statement B, and in fact, I won't do the proof of this one here. I will do the proof of the value of my conditional expectation here, okay? I will do a little bit less. So just have a look on what we have to do in general, okay, if I want to compute a conditional expectation. So in general, if I want to compute my conditional expectation, I need to know, okay, the conditional distribution function. And I know from the course that in order, a priori, to compute the conditional density of x1 given x2 is equal to small x, I know what is this. It is the joint density function. Divided by the density function of x2, where, so it's an x2 here, where the density function of x2 is simply obtained from the joint density function, computing the partial integral with respect to x1. So here, a priori, you can do everything. You can do everything. The only problem is that I can do everything, but the computation is not nice, in fact. But it's a very good exercise to try to do it at home by yourself. And why you are able to do it at home by yourself, if you have time and if you do careful computation, it's that I have, from this one, I have the joint distribution. It is obtained by this quantity. So in the case where n equal to 2, that is the case of the statement B, I have a simpler expression for this one that I can develop, okay? And you can have this part for the conditional density, and then what you have to do, you have to compute the integral of this joint density you obtain here with respect to x1. It will give you f of x2 at the point x2 here, and computing the ratio of these two quantities, you will obtain exactly this conditional distribution, and you will recognize, okay, a Gaussian density function for the conditional density function. But try to do, but you will see that it will be a little bit complicated, okay? Not complicated, but heavy computation in order to do this. And why this computation is heavy? In particular, because I have to compute sigma minus 1 here, okay? Where sigma is the variance-covariance matrix, okay? And let me do a remark in this situation. So in the statement B, I am in the case where n is equal to 2. And my question is just, okay, are you able to compute? So if I have a matrix A, that is A, B, C, D. I know that I have a closed form expression for the determinant here of this matrix, that is A times D minus B. So A times D minus B times C. Okay, this is the determinant. And the question is that, okay, if the determinant of A is different from 0, okay, I want, so I know that A is bijective, so I want to be able to compute A minus 1. Okay? So it's possible to do this in several ways, okay? But in the case where n is equal to 2, you have a nice way to do this. You have a nice way to do this. So I just want to be sure that it records, okay? Oh, I have. So just because I am not sure that, yeah, I have done a mistake here. I am sorry about this because, okay, so I have forgotten to do this. I have to partage my screen, okay? Okay, so I have taken, okay, 120 minutes without the board, okay? So sorry about this. Okay, so just to be sure, because I don't see me. Okay, so I won't record a new video for this, but just have a look on what I have said. So you have my video, okay, with me talking, okay? And for the proof of, so for this one, it was okay. And for my remark concerning the proposition 27, okay? So for this, you have the audio and you don't have the video. But I will send you the slide of the virtual board, so you will be able, okay, having the slide and my video, to be able, okay, to see what I have said. Okay, so I have done a remark concerning this one. Okay, typically. So you will be able to see on the slide 22 and the slide 24, okay? And now I just say that why in general computing this conditional density here is a little bit complicated. It's a little bit complicated because I have to compute this ratio as usual, where the density of x2 is given by the partial integral of the joint density with respect to x1. The joint density here is obtained from this formula, okay, as I have said previously, but without the video, okay. And here I see that I have to compute what? A determinant and an inverse matrix here. So I just say that when you have a matrix of size n equal to 2, okay, that is exactly what happened in the statement of the statement B of proposition 27, because I have only 2 random variables here. I have a random vector of size 2. I have a way in order to do this efficiently, okay? So first, the determinant, you have this nice formula. And my question is how to compute a minus 1 in this situation here. And in this situation, okay, in the size n equal to 2, I can use the following. So it's a result from linear algebra that we call the little Cayley-Hamilton theorem. The little Cayley-Hamilton theorem that will tell you that if you are a matrix of size 2, then you fulfill necessarily this equality. So A squared minus the trace of A times A plus the determinant of A times the identity function of size 2, this has to be equal to 0. So it's a classical result of linear algebra, okay? But in the case where n equal to 2, it is sufficient to compute this term and to see that at the end you obtain 0. I just remind you that what we call the trace of A in this situation is equal to A plus D. It's just the sum of the term on the diagonal here, okay? So why I remind you this little result? I remind you this little result because if my determinant is not 0, meaning that I am bijective, okay, I can handle a little these things to say that I can put A into factor to obtain this one that is equal to, okay, so I can divide by this one, put a minus before, divide by the determinant of A, and I have the right to divide because my determinant is not 0, and I obtain identity of 2. Okay, so from this relation, okay, I can obtain this one. I just make this one pass this way, okay, put A into factor and divide by the determinant of A. And from this little relation, I can deduce what is A minus 1, because the inverse of A, so the inverse of A in this situation will be given by this quantity multiplied by this one. You have here A minus 1 that is given by the trace of A, identity in size 2, minus A over the determinant of A. And it allows you, okay, in the case where n is equal to 2, to obtain very basically the inverse of a matrix from this relation. And then you can plug it inside this formula for the variance covariance matrix. Using this trick, you are able to compute its inverse. You have an expression that will be not a nice expression, but an expression that is a little bit complicated, but possible to handle. And once you will have this one, you will be able to compute this integral. And so to obtain this and doing the ratio, you will recover this result here. Okay. I won't do this computation because, okay, it's a computation that is a little bit heavy. Okay. And I don't want to spend time on it. But what I will want to show you is how to compute this conditional expectation here, even if, okay, I don't have done the computation of the conditional density function. So what I want to do is the following. So I want to compute the conditional expectation of x1 given x2 in the case, so I want to prove and to find this one, okay? So what is the formula I want to prove, okay? So let's write it in details. It will be mu1 plus rho 1, 2, and I will explicit all this term after, okay, of sigma 1 over sigma 2, okay, x2 minus mu2, where the vector of expectation for the vector x1, x2 is just mu1, mu2. The variance covariance matrix for x is given by sigma 1 square, sigma 2 square covariance between x1 and x2 here. And the same here because I have a symmetric matrix, okay? So I have the same terms here, okay? And what I define as rho of 1, 2 is just the covariance between x1 and x2 over sigma 1 and sigma 2, okay? So I have this. It's what I want to prove, in fact. It's what I want to prove. So just a remark, if x1 is independent of x2, I know from my course on conditional expectation that the conditional expectation of x1 given x2 is equal simply to the expectation of x1, that is equal to mu1. And of course, I obtain this formula because in the case where I have independence, the covariance is 0. So this term is equal to 0, and I recover simply mu1. Okay, so in the case of independence, I have this formula that is a basic application of properties concerning conditional expectation. The fact that in the case of the independence between x1 and x2, the conditional expectation of x1 given x2 is none other than the expectation. Okay, so the idea will be to use this kind of property in order to compute, okay, in grid generality. So I just keep this in mind, okay? So I have my vector x1, x2 here, okay? I have my vector x1, x2 with this characteristic here, okay? So here, the idea will be, okay, to build a vector of this form here, y1, x2, where y1 is built this way. So excuse me, I will do the job this way so I can erase. A vector of this form here, A plus B y1 plus C x2, okay, so this vector, okay, and I want, and I impose for y1 to be n01, and I suppose that y1 is independent of x2. Okay, so I want to modify, in some sense, the initial vector, building a new one that takes this form here, okay? So let's study a little this vector here. Okay, so if I denote this vector by y, What is, so I know that it is a Gaussian vector because y1 and y2 are independent. So if I take linear, so this vector first is Gaussian. So if I want to characterize the distribution of the vector in green, I need just to know what is its expectation. So what is expectation of y? Expectation of y is simply a vector where I have inside the expectation of this term. So I have a plus a 0 because the expectation of y1 is 0 plus c, the expectation of x2. And I can write directly that the expectation of x2 is what? Expectation of x2 is equal to mu2. What is the expectation of the second? It's simply mu2. What is the variance covariance matrix of y? First, I have the variance of this term here. I have the variance of this term, keeping in mind that y1 and x2 are independent. So the variance of this first term here is equal to what? Is equal to b squared, because the variance of y1 is equal to 1, plus c squared, the variance of x2, the variance of x2 that is equal to sigma 2 square. Okay? What is the variance of x2 here? It's sigma 2 square. Okay, so I have this. And what is the covariance between these two? By y1 and x2 being independent, the covariance between these two terms will be 0, and it remains the covariance between these two. And I obtain here, as the covariance, I obtain C, okay, the expectation of, C, the variance of x2, that is equal to sigma 2 square. Why I do this? In fact, I have defined this new vector here in order to be able to compute. Keep in mind that I want to compute this conditional expectation here. And the idea, I have flexibility in the choice of my A, my B, and my C here. I want to find A, B, and C in such a way that this Gaussian vector has exactly the same distribution as this one, okay? I want to choose my A, my B, and my C, if it's possible, in order to make this Gaussian vector having the same distribution as this one. And I know that for two Gaussian vectors to have the same distribution, it's sufficient for them to have the same expectation and the same variance covariance matrix. So if I solve this, I obtain a system, okay, that tell me that this expectation has to be equal to mu1. So I'm looking for A, B, and C in such a way that A plus C mu2 is equal to mu1. Then, so I have sigma square here, no problem. So for my covariance, I want to have that C sigma 2 square is equal to what? But the covariance between x1 and x2. And finally, I want that b square plus c square sigma 2 square is equal to, so this term will be equal to this one, that is equal to sigma 1 square. Okay? So I have this A plus C mu2 that is equal to mu1, B square, okay, plus C square sigma 2 square that is equal to this one, okay, and C times sigma 2 square that is equal to this expression here. Okay? And if I solve this system for A, B, and C, I am sure to have here two Gaussian vectors that will have exactly the same distribution. So let's continue here. Okay, so I have this one I will erase some part. So I want to prove this one. Okay, so what can I erase here? But I can erase this one. Okay, and my job now is to solve this one. So I don't have the choice for C. C is equal to what? It's equal to the covariance between x1 and x2 over sigma 2 square. So I obtain this one for C. Okay. I hope that I don't have done mistake, but I will see this at the end. Okay, I obtain for B. What I obtain for B? I just want to be sure not to do mistakes here. Okay, just let me 1 second. Okay, I will check with my notes. Okay, because I don't want to do mistake in the computation. Okay, so what I have done here. Okay, so I have A plus C mu2 that is equal to mu1, that is okay. I have B square plus C square sigma 2 square that is equal to sigma 1 square, no problem. And I have C sigma 2 square that is equal to the covariance. Okay, so I have C that is equal to this one. Okay, no problem. Okay, I have A that is equal to what? The A may be obtained from the fact that it is equal to mu1, okay, minus C, that is the covariance between x1 and x2 over sigma 2 square. And I use this one here. A is equal to mu1 minus C mu2, and minus C mu2 is equal to this one times mu2. And I have for B, okay, by B square is equal to sigma 1 square minus C square sigma 2 square, where the C here is given by this expression here. Okay, so I have solved my system. So what can I do now? Keep in mind that I want to compute the conditional expectation of x1 given x2. Why I have done this job here, defining this new vector? Because I know that this Gaussian vector has the same distribution as this one if I impose this condition on the coefficient A, B, and C. So it means that if I want to compute this conditional expectation here, it's the same conditional expectation as the conditional expectation of what? Of y1 given y2. Because these two vectors have the same distribution, so the conditional expectation of x1 given x2 will be simply the conditional expectation of this term given this one. So I have to compute the conditional expectation of A plus B y1 plus C x2 given x2. But now it will be nice to compute conditional expectation here. Why it will be nice? Because I have the so I can use the linearity of the conditional expectation. The conditional expectation of the constant is equal to A plus what? Plus the conditional expectation of this term, but y1 is independent of x2. y1 is independent of x2, so the conditional expectation is just the expectation of this term, but I know that y1 follows the n01. So this one, okay, has an expectation equal to 0. So it's A plus 0 plus what? Plus C times the expectation of x2 given x2, but x2 being a function of x2, I have here simply C times x2. Okay, so let's continue. So what I have obtained now, okay, I have obtained that the conditional expectation of x1 given x2 is given by this expression, so I can erase this here. Just using the properties of conditional expectation. And that's why I have introduced this new vector y in order to be able to do the computation, not to compute explicitly the conditional density of x1 given x2, but using simply the basic property of the conditional expectation. So if I replace here, I have obtained that the expectation of x1 given x2 is equal to a plus c times x2. What is a? A is this one. It's mu1 minus the covariance between x1 and x2 mu2 over sigma 2 square. So it is the small a here obtained from this expression that I have just copied here, plus what is c? C is simply this one, covariance x1, x2 over sigma 2 square times x2. And if I don't have done mistakes, what I obtain exactly what I want to obtain, that is this term. If I define as ρ1, 2, okay, the covariance between x1, x2 over sigma 1, sigma 2, if I do this here, I will obtain exactly mu1 plus what? x2 minus mu2 multiply by this term here, and covariance x1, x2 over sigma 2 square may be expressed using this one, and it is just sigma ρ1, 2, sigma 1 over sigma 2. So it means that I have proved exactly what I want. My initial aim was to prove this, and it's exactly what I have done this. And keep in mind that the key point of my reasoning was I don't want to compute the conditional density of x1 given x2 because the computations are boring. So in order to do so, okay, I build a new Gaussian vector with the same characteristic of this one, that is with the same distribution, in order to find, okay, this, I impose this form and I choose the good A, B, and C. And now to compute the conditional expectation of the first component with respect to the second, it is sufficient for me to compute the conditional expectation of this first component with respect to the second, because these two vectors have the same distribution. And then now this computation is very easy because I can use the properties of conditional expectation with respect to independence typically. Okay, so I obtain this term, and finishing, okay, to plug inside A and C, I recover exactly the expression I want to obtain. Okay, so I don't have done the whole proof of this proposition here, but I have done the proof of the fact that the conditional expectation is given by this expression here. Okay, so if you want to do the proof, it's possible, okay, doing what I have said here. Okay, it's a boring computation, but you can try to do using what I have explained here concerning how to compute the inverse of a matrix of size 2. Okay, so the course is finished, but nevertheless, I want to introduce some complementary material, okay, that won't be at the program of the final exam, okay, but I want to say things, okay, about the variance-covariance matrix, its properties, and what we can deduce from this, okay? So let's see that it's complementary material here. Complementary material. Okay. So this is, okay, the matrix of size n. This one, okay? We have seen together that the variance of what? A linear combination that is the variance of x prime times capital X. Okay. This may be defined as x prime x small x. Okay. So it implies that for all x belonging to R to the power n, x prime x is positive. It's a strong property because here it's true for any x belonging to R to the power n, independently of the sign of the components of small x here. Okay. So if you have done a little of linear algebra, this means that in fact the matrix X is a positive matrix. It's what we called a positive matrix here. Okay. Knowing that this matrix is also symmetric here, you have a matrix that is symmetric and positive. In particular, from linear algebra, if you have a matrix that is a positive matrix, the determinant of X, oh, excuse me, I have done a misprint here, excuse me. So it's not X here, okay? It's var of X, the variance of X. Here, variance of X. And so the variance covariance matrix is a positive matrix, okay? And it implies that the determinant of the variance covariance matrix, that is var of X, is always positive. So if you have a matrix that is positive and symmetric in this sense here, you can prove that its determinant is a positive number. Okay. What is the consequence of this for n equal to 2? For n equal to 2, okay, my variance covariance matrix is simply variance of x1, variance of x2, covariance between x1 and x2. Okay, so what is the determinant of var of x in this situation here? This determinant is simply equal to this one times this one minus this one times this one, that is variance of x1, variance of x2 minus the covariance between x1 and x2 square. And I know that this determinant, according to what I have said here, this determinant is positive. Okay, so it implies, in fact, a relation. Since this determinant is positive, okay, it implies a relation that is that the covariance between x1 and x2 square has to be less than the variance of x1 and the variance of x2. Implying, if I take the square root in this inequality, and I have the right because I have positive quantity here, I have the absolute value of the covariance between x1 and x2 that is less than the variance of x1 square root, the variance of x2 square root. So from the fact that the variance covariance matrix has some property that is to be symmetric and to be positive in the sense of the matrix, and you know this notion because you do a course of optimization for most of you, and you know that when you want to optimize a mapping from R square into R, okay, you have to solve the Euler conditions to find the possible candidates for being a mean or a max. And to check if you have a mean or a max, okay, you have to consider the Hessian matrix, that is the matrix of the second derivative, and you check if this matrix that is symmetric according to the lemma of Schwarz, the Schwarz lemma, okay, you have to check if it is, okay, definite positive, okay, definite negative or not. So you have already heard about to be positive or to be negative, at the very least, okay, in the course of Philipp-Bishin optimization, okay? So from the property of the fact that the variance covariance matrix is a positive matrix, okay, I obtain this inequality here. This inequality that is in fact an inequality that is true for any x1 in x2 in L2. So I just write here the inequality I have proved, in fact, from the property is that the covariance between x1 and x2 here is less than the square root of the variance of x1 square root the variance of x2. Okay. This inequality, in fact, has a name. This inequality has a name. It is true for any x1 belonging to L2, and it is true for any x2 belonging to L2. This inequality has a name and is called the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality. So in general, okay, in textbook, this inequality don't take in general this form, but the following one. Define x1 tilde that is equal to x1 plus the expectation of x1 and x2 tilde just, it's not what I want to do, in fact. So I put a minus here. Excuse me, just have a look on what I want to do here. Yes, I define this way. x2 minus the expectation of x2. So if I write this inequality, and if I try to express in terms of x1 tilde and x2 tilde, okay, I have the following. So giving these notations here, I have the covariance, that is just the expectation of x1 tilde, x2 tilde, that is less than, okay, the square root of the expectation of x1 tilde square, the square root of expectation of x2 tilde square. Okay, so in general, in textbooks, okay, what we call the Cauchy-Schwarz inequality take this form. Okay, that is just a variant of what I have proved here using the fact that the variance covariance matrix is a matrix that is positive, and so that has a determinant that is positive. Okay, so, okay, in general, okay, it's the usual form for all x1 tilde belonging to L2, and for all x2 tilde belonging to L2, it's the usual form of what we call the Cauchy-Schwarz inequality. And here I have proved it, okay, using the property of the variance covariance matrix that is known to be a positive one, okay, and with a few of linear algebra, I have the job. Okay, so it was the beginning of my complementary material, okay? It was the beginning of my complementary material. I continue. In what we have done previously, I have often used this quantity here. Excuse me, so for x and y belonging to L2. So I define D as so this one, so just to be sure, okay. So just to be sure if I put the square root or not, okay. I put the square root. Excuse me. Yes, I put the square root. Okay. So I have this. I have already introduced this quantity in two situations. Keep in mind that we have proved together that the minimum for A belonging to R of the expectation of x minus A square, okay, we have seen that this minimum here is reached for small a is equal to the expectation of x. And I have given to you an interpretation of the expectation in terms of the best approximation of x in this sense that you can obtain, okay, using constants. So with my notation here you have the minimum between d of x and a square, okay? So the expectation here is the one that minimizes, in fact, the point where this one is minimal for a equal to the expectation of x. Okay? In the same way, we have done the same thing for the conditional expectation. For the conditional expectation, I have considered this. And we have proved together at the end of the chapter concerning conditional expectation that if I want to minimize this quantity, that is, if I want to approximate in this sense x by a function of y, the minimum is reached for the conditional expectation of x given y. And if I continue my analogy here, d of x psi of y minimal for psi of y that is equal to the conditional expectation of x given y. So just one remark here. When I do this interpretation in terms of best approximation, in some sense, okay, I have in mind that when I speak about best approximation, it is the one that minimizes this quantity, but I have in mind that this quantity is related to a distance. And what we are going to prove now is that this quantity defined this way is a distance in the classical sense of topology, okay? So it's what I want to prove, and it will give some sense to this intuitive notion I have given to you concerning expectation and conditional expectation, okay? Because in fact, the related quantity that I minimize in both expressions are in fact related to distance, okay? So I continue. I add a new page, my slide here. So I am interested in d of xy that is equal to the square root of the expectation of x minus y square, okay? And here, in fact, my d is defined from L2 times L2 into R plus. So if you have done, so I want to prove that d is a distance. Okay. What is the meaning of a distance? If I am a distance, I need to check 3 points. First, I need to be symmetric. The distance between x and y has to be equal to the distance between y and x. Here, no problem. It's okay. Why it's okay? Because if I change x and y inside here, I have no problem. Okay, I have no problem. If I change x and y, I obtain this. Second definition, the distance between x and x is equal to 0. Oh, excuse me. The distance between x and y is equal to 0 if and only if x is equal to y in the sense of probability, that is the probability here that x is equal to y has to be equal to 1. Okay, so why I have this? So here it's a little bit more tricky. It's just a result of expectation result. So one side is obvious. This one is okay without problem, because if they are equal with proba 1, this one is 0 with proba 1, and the expectation of something that is 0 will be 0. Okay, so for this side is okay. What happened for the other? So for the other, so for this side here, if I have this, it means that the expectation of x minus y square is 0. Okay, so you have the expectation of a quantity that is positive here, that is 0. And you don't have the choice here. It means that what you have inside, since I have the expectation of something positive that is 0, what you have inside is 0 with proba 1. And so the probability that x is equal to y is equal to 1. Okay? It's because the expectation of a positive random variable is 0 if and only if this random variable is equal to 0. Okay? Because if you take at least one point that is not, that is strictly positive, okay, you will build an expectation that is strictly positive. And the last point in the definition of distance is what we call, I will call it IT or TI, triangular inequality. That is that d of xy is always less than d of xz plus d of zy. Okay, or if I do a picture here, so if you interpret d as a classical distance, so you have x and y here. So in the classical sense, the distance is given by the size of this portion of line here. If I take a z here, this triangular inequality just means that to go from x to y, okay, it's shorter than to go from x to z, and then to go to z from y. Okay, so here you have what I have in red here in my computation, and in black this one, and the distance between x and y, okay, will be shorter than to pass from another point x. Okay. So why I have this in this particular situation here? So I continue here. So I want to prove that d of x, y is less than d of x, z plus d of z, y, where d of xy is defined as the square root of the expectation of the difference of the square. Okay. So I have to prove this. We are going to prove an intermediate result. Okay. So we are going to prove this one, kind of lemma, let's say. This lemma is called the Minkowski inequality. It's a particular case of the Minkowski inequality that tells me this one, that the expectation of x1 plus x2 square to the power 1/2 is always less than the expectation of this one plus the expectation of x2 square to the power 1/2. Okay? And I want to prove this lemma. But before to do the proof, what happens if I suppose that this lemma is okay? Now, if this lemma is okay, I can do the following. If I take for x1, okay, I will take it to be x minus z. If I take for x2, y minus z, the lemma give me what? So I apply. The lemma give me that the expectation of x minus y square 1/2 is less than what? The expectation of x minus z square 1/2 plus the expectation of z minus y square 1/2. And I see that if my lemma is okay, applying this lemma to x1 equal to x minus z and to x2 equal to y minus z here, then I obtain this inequality. And what is this inequality? This inequality here is exactly this one, exactly this one. Okay, so if I prove my lemma, I will have proved that I have the triangular inequality for D. That is the only missing point to prove that D is a distance in the sense of classical topology. Okay, so let's do the proof. I do the proof. What happened for this proof? So I want to prove this, okay? Since I have positive number here, to prove what I want, so to prove star here is equivalent to prove the same thing with a square, okay? Because the square mapping, okay, is strictly increasing on R plus, okay, and in particular bijective. So I can say that what I am interested in is this one. So the square of this quantity here. Okay, square. I just put a square in this inequality. I obtain something that is equivalent because I deal with positive numbers here. Okay, so let's develop what is this one. Well, this one is what? It's the expectation of x1 square plus the expectation of x2 square plus 2 times, okay, I can write it this way, the expectation of x1, x2, okay, this one. And in the same way, okay, since I have a square here, I can also put, okay, absolute value here. That doesn't change nothing, so I can put absolute value, change nothing in this situation here, okay, because I have a square here. Once again, if I develop this square here, I obtain what? I obtain expectation of x1 square, because it's the square of the square root, plus the expectation of x2 square, plus 2 times what? The square root of exponential x1 square, expectation of x2 square. And I see that if I want to prove this inequality, since this term here is equal to this one, and since I have the 2 here and the 2 here, okay, my inequality here is in fact equivalent to prove that this term is less than this one. So if I summarize, to prove this inequality that will give me the fact that D is a distance because it will fulfill the triangular inequality, I just need to prove this one here. But in fact, I have already proved this one. What is this one? Okay, it's what I call here the Cauchy-Schwarz inequality. It's the Cauchy-Schwarz inequality I have written here. So if I summarize, why this complementary material? This complementary material because we have dealt in this lesson with the variance-covariance matrix, proving that this matrix has some property that is symmetric because the covariance is symmetric, and that is positive in the sense of the matrix because I have this inequality here. And so, since I have a symmetric matrix that is positive, I know from linear algebra, it's the only thing that I have supposed here, that its determinant is positive. The fact that its determinant is positive, if I apply it for n equal to 2, give me an inequality that I have called the Cauchy-Schwarz inequality. That is this one. Okay? That is a classical, okay, inequality for expectations. Okay. So it's an inequality. What may be its help? But its help may be to give more sense to some intuition I have given, or I've tried to give to you in this course concerning the interpretation of the expectation of X as the best approximation of X in terms of constant, and an interpretation of the expectation, the conditional expectation as best approximation by mappings depending on Y. The conditional expectation of X given Y is the best approximation of X by mapping depending on Y. Keep in mind also that in the terms of optimal linear predictors, okay, I have also given to you an interpretation of the best optimal linear as the mapping that is affine in Y that best approximate capital X. But when I have spoken in terms of best approximation, what was the underlying notion that I have used in order to speak about approximation? This underlying notion was the expectation of the difference of the square. Okay, so the expectation of the difference of the square. I have minimized this quantity. Okay, I have minimized this quantity. And I want just to give more sense to this approximation point of view. I just say that, in fact, here you have square of distances if I define the distance between two random variables in L2 this way. Okay, so expectation is the one that minimizes the distance if I do the optimization over constant. Conditional expectation is the one that minimizes the distance if I do optimization with respect to function of Y. And what I have proved here is to use the Cauchy-Schwarz inequality to prove that D is really a distance in the sense of topology. So in the sense of topology, a distance is what? Something that is symmetric, that fulfills the fact that the distance between 2 points is 0 if and only if these 2 points are equal, and something that fulfills the triangular inequality. And if I want to prove the triangular inequality here, the way to do the proof is the last slide of today, is the proof of this lemma, that is just, in fact, the Cauchy-Schwarz inequality. Okay, so this complementary material that I won't consider into account for the program of the final exam, but will be just to give you more sense to the interpretation of expectation, conditional expectation, and optimal linear predictors in terms of best approximations. Okay, and you will see also that in the statistical part that we are going to start together next week, I will use also this quantity, the distance D, in fact, the underlying distance D, in order to compare the quality of some approximation I can do of quantity of interest in statistics. Okay, so it closes the course and the video. So you have seen that I have a little problem in this video during 20 minutes, but it is just for an anecdotic part of the course. So I will explain to you in an email, okay, how to cope with this little problem. So see you next week, or see you, in fact, next Thursday for the live online session. Bye-bye.